Gradient descent is probably the most famous optimization algorithm in machine learning. And at first glance, it seems almost trivial. Take your current point, compute the gradient, and move a little bit in the opposite direction. But don't be fooled by its simplicity. This tiny update rule hides at least three very different ideas: a geometric one, a dynamical one, and an analytical one, all of which we will cover in this video. First, imagine you are a lonely algorithm sitting on a lost landscape, trying to find the minimum. Unlucky as you are, you only have access to local information. That is, you basically can only observe the function at your given point, and you do not see anything else. So, what is your strategy to find the minimum anyways? A straightforward idea would be the following. Be a greedy algorithm and always follow the locally most promising direction. But what does this actually mean? So, to do this, you first have to specify what actually qualifies as a promising direction. But this is also straightforward. Since you want to minimize the loss, the best direction should be the one that yields the strongest decrease in the objective. And to figure out how the objective changes in a given direction v, we look at the directional derivative in this direction, which is given by the scalar product between the gradient of f and v. And then we try to minimize this directional derivative with respect to the direction v. But to have a fair comparison and a useful minimization problem here, we only look at directions that are comparable in terms of their norm. For example, all vectors of norm 1. So this gives us a constrained linear optimization problem, which we can solve quite easily by using Lagrange multipliers. And if we do this, we find that the locally most promising direction is simply given by the negative gradient of f at x. So to turn this insight finally into an algorithm, we simply step a little bit into this locally optimal direction, and as you know, the result is called gradient descent. In the steepest descent interpretation, we figured out that the locally optimal direction to move in is the negative gradient, and that we probably should not take a too large step, as it is only a local choice. But have you ever wondered what happens if we use an infinitesimal small step? To see what happens, we first have to realize that the gradient of the objective function defines a vector field on the optimization space, and for such a vector field we can define a corresponding ordinary differential equation whose solutions follow the vector field, and which, in the case of the gradient, is the so-called gradient flow. And indeed, if we simply rearrange the formula for gradient descent, we can find this ODE. First, subtract the iterate xt, then divide by the step size alpha to see that the left-hand side is the difference quotient of the current location, and then push the step size to 0 to find that the time derivative of the current location, so the velocity of the current iterate, is given by the negative gradient at that point. And that means that the iterate always points downhill with a speed proportional to the gradient magnitude, such that it is faster in steeper regions and slower in flat ones. Now, what happens if we actually follow this flow with the algorithm? To find out, let's simply compute the time derivative of the function values along the trajectory. By the chain rule, this is simply given by the dot product of the gradient and x dot of t. But along the ODE, x dot of t is simply the negative gradient, such that this equates to minus the squared gradient norm. And this is quite beautiful. It tells us that along the trajectory, the objective can never increase, and the only way the flow can stop is when the gradient vanishes, that is, at a stationary point. Now that we've seen this, the next natural question is the following. How do we get gradient descent back from the gradient flow? Obviously, we simply discretize the ODE again. if we apply the explicit Euler discretization to the gradient flow, we exactly end up with gradient descent. And in this interpretation, the step size is the time discretization step of the underlying differential equation. And how to choose it correctly, such that this discretization is stable and fast, is easiest seen with the next perspective. To motivate this last perspective, let's say you want to minimize a simple one-dimensional quadratic function of the form 1/2 times a times x minus x star squared. So a quadratic with minimizer x star and curvature a. To find the minimizer algorithmically as before, we simply compute the derivative, which here is given by a times x minus x star. So no matter at which point we are, the negative gradient always points directly onto the minimum. And that means that we actually know the optimal direction to move along. And we only have to figure out how large our step should be that we take into this direction. So how can we find it? In this one-dimensional case, it's actually pretty simple. Since x1 should be the same as x star, we should move exactly a distance of x star minus x0. And if we compare this to our formula for the gradient, this leaves us with the choice of 1/a as step size, such that gradient descent minimizes the simple quadratic function in one step. And now we can turn this perspective upside down. If we are given an objective function f, and we perform one step of gradient descent with a given step size, we can find a quadratic approximation to f that would be minimized by this step. If we bring everything from the update step on the same side, we get this formula that equates to 0, which then can be interpreted as the first order optimality condition of the given quadratic approximation, which consists of a linearization around x0 plus some quadratic regularization term with curvature 1/2 times the step size. And that means that we can actually interpret each step of gradient descent as the minimization of a quadratic approximation to our objective function, such that running gradient descent is equivalent to sequential quadratic minimization. Okay, so to be honest, the first time I saw this perspective, I thought it to be a little bit made up, and I was not really sure what to do with it. But it is actually quite powerful. To see how this perspective might help, let's look at what happens if we increase or decrease the step size parameter. If we decrease the step size, the quadratic gets steeper as the curvature grows, and the minimum is closer to x0. And if we increase the step size, the opposite happens. But did you notice something? For small step sizes, the quadratic lies above the function everywhere. And if we increase further and further, there comes a point where it actually crosses the objective and lies partly below the objective function. And this insight can be used quite nicely if you combine it with the right assumptions on the objective function. Namely, since the gradient step minimizes this simple quadratic approximation to our function, it would be quite helpful if we could bound the objective function at every point from above by such a quadratic, such that if we minimize this quadratic upper bound with each gradient step, we directly ensure that this also leads to a decrease in the objective itself. And at the heart of this idea is the so-called Descent Lemma, which states that if the gradient of the objective function is L Lipschitz continuous, so the gradient can change at most linearly with slope L, then the absolute difference between the objective function and its linearization around a given point can grow at most quadratically with curvature L. And that means that at every point x, I get a quadratic majorand and a quadratic minorand to my objective function, which are given by the linearization plus or minus the quadratic term with curvature L. And that finally means that if we are at a given point x0 and we perform a step of gradient descent with step size 1/L, then this step minimizes exactly the quadratic upper bound given by the descent lemma, and since it always lies above the objective, the decrease in the objective itself always needs to be greater or equal to the decrease in the quadratic approximation. And with this insight, you are already halfway through the convergence proof of gradient descent. So, to summarize, while gradient descent looks pretty simple in the beginning, one can actually develop a lot of nice and beautiful theory based on it. You can interpret it as a greedy algorithm, as the discretization of an ODE, or as sequential quadratic minimization, and depending on what you are trying to understand, one or the other perspective might be more helpful. So, as always, if you have any questions, comments, or you just want to chat a little, don't hesitate to reach out in the comments. Besides that, I hope you liked the video and you could learn something from it, and thanks for watching.